welcome. My name is Eric. I'm an engineer / tech lead on the web performance team in the Android org at Google. I work out of the London office. And I sit very close by the folks that built Perfetto. They are actually an offshoot of our team originally, which is one of the reasons why Chrome is quite prominent in all the Perfetto documentation, and why there's a lot of integration for Perfetto with Chrome today. And I wanted to use this chance mainly because there have been some requests from some folks about, hey, can we learn a little bit more about how to use Perfetto effectively? To talk a little bit about, what can you do with Perfetto? And I'll give you some examples of what we use Perfetto for in our team. After I talk a little bit about instrumentation that exists today in Chrome. Let me try to skip over the slides quickly because I think context. I'd like to get into the demo aspect, where it's a bit more interactive, hopefully as well, as fast as we can. How familiar are folks with Perfetto? A little bit. Users. Somebody's heard of it. That's great. So
use it every day.
Use it every day. Yeah, that's what I like to hear, right? So I think the main pieces of Perfetto are on the slide. The crux is there is a lot of support for instrumentation, both in an application like Chrome, as well as on the system side. On Android, it's really heavily integrated nowadays. You get a ton of data sources from the system with Perfetto. You get some tools on top of this that help you analyze traces. It's a SQL-based trace processor. That trace processor is quite capable and extensible with custom metrics. And it's also the foundation of the Perfetto UI, the trace viewer that is effectively a replacement for Chrome / tracing. The trace viewer is also extensible, and we'll talk about this a little bit later. So yeah, what does it look like on Android when you have Chrome and system data sources in a single trace? You get fine-grained details of what's happening within Chrome on the same timeline as, say, scheduling information or stack sampling, heap sampling, in profiling. A lot of different data sources basically, and this allows you to try to align things that happen in Chrome with the system's characteristics and performance. It allows really powerful analysis. We have a bunch of things that are instrumented in Chrome today. Of course, it could always be better, but I think there are some components where it's already quite good. Task scheduling in IPC is one of the prime examples where things actually work really well. You get annotations of different tasks that are running in Chrome on different threads. You get flows in between task posting events. So you can follow along how does the logic of Chrome kind of connect to each other across threads and across processes. There are some optional features in there as well. You can, for example, enable arguments for IPCs to be logged into Perfetto traces too when you record locally. We have similarly extensive instrumentation in the input and graphics pipeline, where effectively the whole input and graphics pipeline is attributed. You can understand what the latencies are of different steps in the pipeline. We have a plugin that I'll show you later that helps identify when there are janks and scrolls. And you get a lot of just debugging data into why did the graphics state machine decide to do a certain operation versus another one. In navigation, we have fundamental instrumentation. I'd say I think there could be better instrumentation in that area. In theory, you can follow along where performance issues are in navigation and maybe identify some opportunities there too using Perfetto data. And then there are lots of other teams that have started to build sort of domain-specific pieces into Chrome's instrumentation. Like in V8, you can get runtime call stats, which is how much time do you spend compiling versus executing versus garbage collecting, etc. In Blink, there's more rendering annotations, more rendering events, and you get a few other data sources too. So that's what's available today. If you want to instrument your own code, you can get started with quite simple mechanisms. You have scoped events that effectively just create a begin of a slice that lasts until the trace event goes out of scope. That's why they call them scoped trace events. You have additional advanced features where you can provide custom tracks to track events, to trace events that allow you to track async state. You have support for structured arguments, so data types that are more complex. You can create flow events between trace events. And I guess what that looks like in a minute. The Perfetto documentation is quite extensive on this. It's not really Chrome specific. These features, you can build them into any application that likes to trace. Then I want to touch briefly before we go into demos on Perfetto is this extensible platform, right? You can emit pretty unstructured data. You just dump it into a trace. What you do with that is then up to you. You can build plugins into the Perfetto UI, for example, that help you visualize this dump of data in a way that you can actually make sense of it. This is an example of something that we prototype but haven't actually shipped yet. So there's more work to be done. And this is why I'm saying it in navigation. Actually, maybe there's more things that we can do. This is basically a mechanism that tries to read the frame tree node tree and convert it into a data structure that you can navigate more easily and can understand more easily. How long did specific render frames live? What content do they host, etc. The data is all there. It's just a matter of visualizing it correctly so that you can make sense of it. And that's what tracing is all about. And I think I'll get started with a scrolling trace to show you what we typically do when we use Perfetto. So this is a trace that one of my engineers recorded of a scroll in Chrome. And the cool thing here is that because of this plugin in Perfetto, I mean, maybe we should talk about the basics, but yeah, you can see the scheduling information up at the top again. We have some CPU tracks as well for the frequencies. So you can look at what does the scheduler do here? Does it ramp up frequencies or not, etc. We've got the scrolljank plugin. I'll talk about that in a moment. And then you have different threads and processes. So this was a trace from Chrome Beta. We've got the browser process here. We've got both the scheduling info. So you get states of, is this thread running or runnable? How long does it take to be scheduled? And you get all these events. These are the task events that I mentioned before. Task scheduling is instrumented well. You see that there are some Mojo events. So this was actually a task that was created because we received a Mojo message, and we had to handle it. Seems like it was a begin frame. So this was rendering related. And then for rendering, you get more events. Here's a graphics event, a graphics pipeline event that connects the different pipeline stages for the graphics subsystem. So you can follow along that as well, see what happened in this vsync, what rendering has been done. You get some, you get events for all the threads, right? And then you get a bunch of async tracks. Some of them are related to loading. Some of them are related to, these are probably mostly loading related. Some of them will be related to rendering, etc. What else? Yeah, you've got the browser process. You've got the privilege process on Android. That's the GPU process, and you've got the renderer process. That's the sandboxed one. And then because it's not always easy to make sense of this data as is, right? We have visualizations on top of this. The one I want to show you here is the scroll visualization. Basically, what we see here is that there are 3 scrolls in this trace. And each of these scrolls are made out of a ton of input events that had been handled and then resulted in a frame production. Each of these event latency sub-events is broken down again into different pipeline stages for input handling as well as rendering. And you can see that when things go well, those events are all quite consistent. Input is received and the frame is produced in roughly the same latency. And you see that so some of these red events, those are event latency that end up actually janking. We dropped the frame, or we didn't manage to produce the result of that input during the scroll in time. For those janky events, you can then look at the scroll janks track to see what was the cause of that jank. The one that I highlighted here is one where you can see that, right? The generation to browser main step took longer than in all the other events. And that's why that jank is attributed to that step. This is something that helps us, these visualizations are also a way for us to compute metrics over traces. So think about basically recording dozens of traces, hundreds of traces, and then running these metrics that build up this visualization to compute, well, what are the top causes of scroll jank? Which ones do I need to go and address, right? Like, is this the one that happens frequently? Or is it just a one-off that happened to happen right now? So we can use this instrumentation both for debugging a single trace, but also to then analyze dozens, hundreds, thousands. Yay. Okay, this is always what you want to have happen, right? So yeah, let me reload that one. All of that instrumentation, as I said, right, like the fundamental data is in the trace. The plugin just helps visualize where there are issues and helps sort of bring it into a user-friendly state. So yeah, what I wanted to show you is that we also have an ability to create additional graphs and insights into what the plugin does, what happens in the scroll. So we have, for example, this fantastic visualization here, which shows you the blue line is basically all the input events that have been received, and the red dots are the presented frames, and they are tracked here on an offset graph across time. So basically, you can see how the finger moves across the screen while the scroll is happening, and you'll see that in the blue portion. Those are the input events, how the finger moves. And the red events are basically how the content behind the finger starts to move. So what you want to see in a graph like this is that both of those lines are close together and follow each other. So this doesn't look too horrible. But you also see that there are some janks. Those are the gray lines, the thicker gray lines. Those indicate where we had frame drops. But you can sometimes also observe, in this case, it's not as prominent, are little yellow dots where effectively Chrome decided to produce a frame, but actually ended up choosing the wrong position of the content on the screen, because it's not always perfect to exactly precisely find the right offset to present when input isn't quite consistent. So yeah, that's the first piece. When you click on one of those janky event latencies, you can also look at the breakdown stage, understand how that compares to the previous and the next latency that's being computed, or sorry, that's been presented. And the big piece here again is it's generation to browser main. That's taking long. So how do we go about debugging what's going on? We'll mark this. Now you need to know a little bit about what does it mean. Generation to browser main is a step that basically means input was created by the OS, and we are trying to receive it on the first Chrome thread that handles it, which is the browser main thread, the browser UI thread. And for some reason, that took a long time. So because I know that, I'm going to look at the browser main thread, and I'm going to look at what's going on here. Seems like the input was handled back here, but for some reason we were really busy beforehand. So I can look at what's happening here. Looks like this is a task that was posted from the segmentation platform's execute database maintenance tasks function. So maybe that's now something I can look at. Actually, what task is this? What does it do? I can also look at all these little triangle events down below here. There are thousands of them. What do they do? So I can select this range, and I can have a look at, well, what is it? What are all these events? I have 5,000 post tasks. Okay, why do we post 5,000 tasks? What do they do? So let's have a look where they go. Seems like they go into the thread pool, and then the thread pool, they do more things. All of this comes from post transaction in the level DB. So it seems like the segmentation platform is doing a lot of work and posts thousands of tasks from the browser main thread. I'd probably now look at the code of that and try to understand, why is this running on the browser main thread? Should it run there? Can I avoid posting 5,000 tasks? Can we do this more efficiently somehow, right? So that's what this plugin enables us to do. I understand when things crank. Why is that the case? All right, changing tack a little bit. The second thing I want to show you is how we can use all this Perfetto data to try and optimize. Like the one thing that we're looking at, which you'll hear a bit more about in the next talk in the big room, is speedometer. We try to make speedometer faster, and for that we need to understand how does it behave. This is a trace of one speedometer 3 run, and as you can expect, in speedometer we have a lot of execution on the renderer main thread. That's the busiest thread here. We can see that also in the CPU scheduling data here. See, our renderer main is really occupying the largest core, the big core on this device during the speedometer run. So one thing that I'd like to know now, right? Speedometer is a collection of tests. How does scheduling look like for these different tests? Are they all behaving similarly? Are there some that behave different to others? So the first thing that I want to do for that is see, when is which subtest on this timeline. For that, we built a little helper into Perfetto. It's basically a custom metric. It's in this module called Chrome Speedometer, and it has a table that's called Chrome Speedometer Measure, and a bunch of columns. And what I'm doing here is really just get all the rows out of this table and create a name column that joins together some of those columns. Then I have events or rows in this table for each of the subtests and the different phases of these subtests. Now there's a cool feature. I can go back to the timeline and I can say, hey, actually I want this in a track. I want this as a debug track, and I can name it speedometer phase. And then I have a track up top that tells me in this interval, this is editor tip tap synchronous phase in the first iteration of speedometer. The way this works under the hood is that speedometer emits some trace events into the trace that tell you when each of these sub-phases starts and stops. It just doesn't do it in a nice visual way, so I have to use a plugin or a custom metric to add a nice track for it. I can be even fancier, and I can make the track a little bit more expressive, a little bit more nested. This is now a query I'm not going to go through in detail, but basically what it does is instead of joining together the string, it tries to create separate events for the different levels in speedometer.
Could you do something like that with performance.mark?
Yes, this is all based on performance.mark, yes.
So what is the Chrome.speedometer for if it's based on performance.mark?
This is a, let me have a look if we can very briefly show what this looks like. So this is a standard library function that effectively goes and finds all of those events that were emitted via performance.mark. Those measures, they end up in here basically. You'd have to look into these submodules to see where actually it ends up being computed. But yeah, you select all of these. You'll select the events out of blink.userTiming category. Those are the performance.mark events.
So this is SQL, and I have pasted all of this directly in that view instead of.
You could have also pasted this all directly in there, but we are committing helpers that are sort of fundamental building blocks. We commit them into Perfetto so that they are available everywhere. Perfetto is open source, so you can do that with anything that helps make sense. For the scrollgen plugin, the same thing happens, right? We have helpers in here that find where all the scrolls. What's the start timestamp? What's the duration of the scroll? That ends up building the data model for the scroll track that we saw earlier.
So Perfetto is a website, right? So it only picks the ones that are checked into Chromium. If I wanted to add my own,
you can add these to Perfetto open source, right? This is in you can either add them to Chrome, where Chrome has its own standard lib, but also there's Perfetto open source where you can add your own metrics too. I don't think there's any requirement. Like we're happy to accept anything that is generally applicable.
Okay.
You can also build your own Perfetto UI if you don't want to commit things. Again, all open source.
So one question from before, can I see vsyncs in the trace? Because that's the thing that I missed from the previous Chrome trace.
I don't think we have that feature yet, but please do file a feature request for it because I would love to.
There's another thing like the thread times. So the wall time and thread time, like the real running time, that is no longer visible anymore. That's one of the major differences.
Oh, is that the? I'm not sure if that's.
It used to be really solid and semi-solid in the previous viewer. So it would tell you how much.
Yeah, that should still be the case. You see,
so the wall time.
You've put the shading here as well for the same.
So previously the wall time, the actual running time, and the CPU time, there were 3 times presented for each function.
Right. You mean in the details?
Yes, in the details.
Yeah, I'm not sure if we have that, but what we do have. I mean, this is a system trace, so things are a little bit different, right? Here you've got the thread duration. I think that comes even in Chrome traces. You should be able to see that.
That comes, but the real CPU time, which was there before, does not come, I think.
Yeah, I mean, the thread time is the CPU duration, right?
Should we interpret it that way?
Yeah, thread time is, this thread duration is the time that this thread spent running on the CPU. It's just not CPU time because it's only for a specific thread.
But there used to be a wall time before, which it's not there.
Yeah. That
is it duration?
Is duration. That's the wall time.
That's the wall time?
Yeah.
Okay.
And in the system trace, because we have scheduling data, you also get breakdowns of how much did it spend in different scheduling states.
Yeah, I mean, typically as we are checking how much time out for performance, we tend to usually rely on that actual CPU time. So now the thread time reflects.
Yeah, the thread time reflects that, yeah.
Okay.
Again, all of this is in the SQL model too, right? All of these events, you can get to them from SQL.
Mm-hmm.
But yeah, what I wanted to show you is now I actually have a grouping of different tests, different suites, different tests, different steps in a nice hierarchical way. That's what this other query did. So, but the really powerful thing comes actually now, right? Like I now know where are different speedometer intervals. I've got thread scheduling data in here. So maybe one thing I'd like to know is, how many threads typically run in individual tests, in individual suites. For that, I can use another helper. Let's first look at the data model that this helper provides, right? This is a helper that computes thread level parallelism. The thing that it really tells you is how many CPUs are active at any certain point in time. The result of a query like this then is at this timestamp, there's 1 CPU active, at another one, that's 3, and so on. Again, we can look at this visually. We can just make it a new debug track. That's a counter debug track this time because I don't have durations, I only have values. I'll show that, and now you see visually how much CPU time. Well, no, sorry, not how much. How many threads were active at any point in time. And yes, you can look at this visually now, but even more fun is it when you start using complex queries to create, aggregations out of all of this. I'm not going to go through the details of the SQL. It will take a lot of time. But the TLDR is, what I'm trying to do here is I'm looking at the different suites of speedometer, because now I have the times when the suites were active. And I'm going to join that with the active CPU counts to understand, well, in Charge.js, for example, how long did I spend with 3 CPUs active, and how long with 8, and so on. I can compute percentages of that, and I can also compute an average overall for Charge.js. And that is maybe an insight that can lead me to look at, well, actually, sorry, this subtest, editor code mirror, it seems to spend actually quite a lot of time with 8 CPU cores running in parallel. And the average active number of CPUs is also pretty high at 5. But maybe there are some others, like this one at the bottom here, to do MVC. You only have 5% with 8 cores, and your average is only 3.5. So that might lead me to look at, well, what's going on there, right? Can I visually look at this? Can I debug it a little bit further? Here's editor code mirror. No, was that the one? I think that was the one, right? Yeah. So in editor code mirror, I can see there were times when there's quite a lot of activity. And I can look at what threads are these that are active in parallel. I can look at what they might be doing. My expectation is that this is actually some thread pool work that happens in parallel. Probably some GC work, something like that. So yeah, let me have a look. Unless I'm breaking the UI now. Looks like that might be. So maybe this is, there we go. Yeah, actually it seems to be that we're compiling. So yeah, maybe now I would need to look at what's V8 doing here. What does this subtest do that other subtests don't do? Is that normal that there are 8 cores running in parallel? This is an insight that maybe can help me understand what I need to optimize for in CodeMirror. I need to optimize for throughput for all these threads as opposed to the one thread. Yeah, so this is an example. I have a bunch of others that kind of show other data sources that you can integrate into analysis like this. A cool one maybe is this trace. This is a trace where we recorded some stack samples together with PMU counters. Those are performance monitors that tell you how many instructions are being executed, how many cycles are being spent. So with this, what we can look at is, well, are there sequences of, say, CI renderer main execution where there's very poor efficiency, very poor utilization of the CPU because a low number of instructions are being executed per cycle. So for that, again, I can look at the SQL model, and I can try and create an IPC track, which basically takes the delta values of the CPU cycle track So also interesting. You can look at the delta values if you'd like, by changing the mode of display here. So you'll see that there are some tests where we're quickly getting through some instructions, and then others where maybe we aren't. But I really want this. I want to know how many instructions are there per cycle being executed. So for that, I have another query that joins those two tracks together and computes the ratio. Again, we know we can create debug tracks, so we can add a new track. It's another new counter. We can plot that, and then we can understand. We can find are there areas where IPC is low. And maybe one thing that you notice is that in the first iteration, IPC is low. Part of the reason here is that in the first iteration, we actually still load the resources from the network and speedometer. And that's why, things aren't really warm, things aren't really in the cache. There's less efficiency in the CPU. But again, I can also then look at, are there specific subtests that are performing pretty poorly? And in particular, I think there was one case in here that was quite cool to look at. In IPC, let me find which one it is. It's chart.js. Yeah, here's an execution of a test while IPC is below 1 for a long period of time. So at this point, I might then be wondering, well, what's being executed here? So the cool thing is in this trace, we also included some call stack sampling. So here I can actually then look at, well, let's find roughly where this IPC region is, where it's so slow, and let me highlight that section and look at, well, what is being executed here, right? Now I have a call stack tree. I can look at, what's happening.
Does the call stack sampling work on all platforms? Or?
So I'm not 100% sure. I believe that on Windows, it's in work in progress. On Unix, it's generally better because all of the things that you need for this is really just a perf trace, right? Perf or simple perf on Android. The trace processor engine can ingest either perf or simple perf, and then align with the timeline. Another thing that you can do is, yet again, just like before, we can try to use this timeline feature to see, well, which of the stack samples fall into which subtest, and we can generate a profile that we can then. It's basically a pprof profile that adds the suite name on top of the call stack as another breakdown of the sample. You get a result here that's a blob. This is basically you're downloading the profile file, and then you can open it. I've opened this earlier in the pprof viewer, and then you basically get a breakdown for each of the subtests out of this particular run. You can, in theory, also use batch trace processing to combine samples from many traces into one of these profiles to get a little bit more higher sample count. And you could also, utilize. I think we don't have all the features in there, but I could imagine places where we then annotate each of these stacks with what was the IPC during this particular stack on average. So you could color the stacks based on that and get another dimension into it. All of that is kind of made possible by having everything together in the timeline, so you can combine all of those data sources. All right, I think I'll stop here. Any questions?
There's this GPU load also, which can be measured. I wonder what are the probes that we use for that?
I don't know. I think Perfetto has support for that, yes. the easiest way to find out about what's available in Perfetto is to look at the recording page. For Android in particular, you've got GPU pieces. Yeah, I guess you get the frequency. But yeah, I'm not familiar with the GPU probes.
And this is the original in Android, for example. It's like systrace is the basis, or they gather data from the same ftrace or from the system.
The fundamental purpose on Android is ftrace that is underlying all of this. We don't really go through the same tooling as systrace because we've got a custom service on Android that collects data from ftrace directly. But the data is the same.
Okay.
On Android, it integrates with trace, which is sort of user space annotations for Android applications. But it also integrates with any of the Perfetto SDK apps like Chrome. So Chrome is able to directly emit into the same trace.
Right. Okay. And like with this data, does it really affect performance? So do you really want to measure speedometer while you take traces?
Yeah. So some of the traces that I showed you today, they had a lot of data sources enabled, right? And those you probably wouldn't use for speedometer profiling if you want to look at PMU stats, for example. You can configure these trace configs depending on what you want to do. We integrate most of our speedometer analysis into Crossbench, which is our Chrome's new benchmarking automation tool, as custom probes. And we've got configurations. Maybe I can try and show you some, but actually we don't have time, I think. So yeah, typically when you want to profile, you'll only enable those data sources that you really need. Everything else adds to overhead. And if you do that, if you do only that, and you use a properly tweaked config, the overhead isn't enormous.
Okay. Yeah, because sometimes those numbers are kind of, when you put on the trace markers, the numbers shoot up. So
for the trace that you were showing, what was the speedometer score regression during recording?
Oh, I don't know. Probably very significant. At least half, maybe more.
In the timeline view, do you use the search box much? Like, are there tips or tricks? Like, I find I just do a simple string and pray. I go through all good things, and eventually I find the victim looking.
Yeah, I think nowadays it searches in the arguments too. So oftentimes, if you know what you're precisely looking for, like the event that you're looking for, if you know that there's only few of those, right? Like, I wouldn't use it to look for input latency, right? Like if there's hundreds, thousands of those events, then it won't help you. But if you're looking for a janky one, or for a one-off marker that you emit yourself into the trace, things like that, then you might want to use it. The biggest use for me for the search box is typing colon so that I can query the trace model underneath. And that is very, very useful, right? So the example here is maybe not as relevant for Chrome, but you can, for example, do something like selecting things from the slice table, which is all of those, and it's all of those events that have starts and end points. You can order by something. You can filter by something.
So if you're not super familiar with the table schemas, where would you recommend someone get started?
In the Perfetto documentation.
And I'm likely to have a good experience doing that.
Oh, maybe I shouldn't have done that. But yeah, here you get 10,000 rows, right? And then you could now actually, you can click on these, you can find them that way. That's how, if you have a lot of data, you can actually do searches based on the things that you want to find. So here's like longest run task, so to say. Yeah, Perfetto documentation should be good for the table models.
Okay.
Sadly there isn't like super great guides for how to use them. But maybe a good documentation in code is looking at all the standard helpers. Because of course they make use of the fundamental data sources, data structures, and tables.
You showed an example of extension visualization for rolling. Where can we look at to see how that works, or to write your own extension? Where the code does that?
Yeah. So that lives in the Perfetto repository. We've got UI, and I think if you look for scroll jank in the UI, you'll probably find that that plugin quite easily. So anything that is related to scroll jank in third-party Perfetto, that's how this all works.
And what does the development experience look like? So if I made a change, how would I
Test it.
test it? Yeah.
Also, I'll refer you to Perfetto docs. Perfetto is a pretty small repository compared to Chrome. It's actually quite quick to get started. You can, develop on your laptop as opposed to needing to use a big workstation. But yeah, there's even a documentation about how to create plugins for the UI. There's instructions for how to get started. There's also a UI development hints section. I think there must be a section in here also how to build the UI. I think it's in here, UI development. So yeah, for the UI, you just download the Git repository, then run a script to install dependencies, build it, and then run a dev server.
And I just see it scroll by quickly and Windows not recommended. Is that?
Windows not recommended? Oh yeah.
There's no quick start guide because it's a pain in the butt.
I mean, building on Windows is supported to a degree, but you can't run the UI from Windows today, I believe.
Okay.
Sorry.
Cool.
Contributions
welcome. Yeah. There you go.
Right. Shall we end here and have a break before the next talk?
Thank you.
Yeah. Thank you.
Thank you.